So this becomes simply phi into phi minus theta, or you can say theta minus phi, because this is theta minus phi. So if you cancel, I will write it in a with a minus sign. So I can write it as theta minus phi, that is better. And we need to take the maximum of this supremum of phi into theta minus phi. The supremum is taken over phi between 0 to theta. So this is a simple function. So if you differentiate and put equal to 0, it is at phi is equal to theta by 2. So that is equal to theta by 2, theta minus theta by 2, that is equal to theta square by 4. So Chapman-Robbins Kiefer lower bound for theta is theta square by 4. Since I have taken here only one observation, I can consider an unbiased estimator as 2x. This is unbiased. And what is variance of 2x? That is theta square by 12 into 4. So that is theta square by 3, which is greater than theta square by 4 here. So CRK lower bound is not attained here. Let me take another application here. Suppose I have an observation from exponential distribution with only minimum guarantee time theta, and we want to calculate for theta. So as before, I will consider fx phi by fx theta. So you need to write it here. In the numerator, we have fx phi. So therefore, I have to consider the region which is smaller in the numerator. So fx phi over fx theta, that is equal to e to the power phi minus x divided by e to the power theta minus x. This is for theta less than phi less than x, and it is 0 for theta less than x less than phi. If I am considering x to be less than theta, then both will be 0. So I will not write that because it is 0 by 0 kind of term there. So now I consider expectation of fx phi over fx theta when the distribution is with parameter theta. So it is integral e to the power, this term it is nothing but phi minus theta, e to the power theta minus x dx from phi to infinity. So this you integrate, it is simply equal to 1. Now similarly, if I consider expectation of fx phi by fx theta whole square, that is equal to phi to infinity e to the power 2 phi minus 2 theta e to the power theta minus x dx. So if you integrate this, this is e to the power phi minus theta. So the term which is coming in the denominator of the CRK bound, it is a phi theta, that is the variance of fx phi by fx theta, that is equal to e to the power phi minus theta minus 1. So we need to write g theta minus g phi whole square divided by a phi theta, that is equal to phi minus theta square divided by e to the power phi minus theta minus 1. Here phi is greater than theta. Okay. So we want to find out supremum of this with respect to phi. So I can put phi minus theta is equal to say t, then it is nothing but t square by e to the power t minus 1. Again, it is a very straightforward function. In your maths 1, etc., you have done this kind of problems. Suppose I call this function as say ht. Okay, this function if I call ht, then you look at the behavior of ht. If I take ht tending to st tending to 0, for example, okay, what happens to this? This is 0 by 0, so you can consider expansion here. So one term will get cancelled out, so you get t in the numerator, so you will actually get 0. Or you can apply L'Hopital rule also, 2t by e to the power t, again which is 0. Similarly, if I consider say limit of this as t tends to infinity, then what happens? Again it is infinity by infinity form, so again we use the same logic, that expansion thing. So if we consider this expansion, then I will get e to the power t, so then that is 1 plus this one. So next step 1, that will get cancelled out. So I should get it is equal to zero. So if I consider g prime t, okay, you have to simplify this little bit. So you can check that g prime t is basically less than 0 for t greater than or equal to 2, and it is greater than 0 for t less than or equal to 1. In between, I don't know. So this h prime t. So h prime t changes sign between 1 and 2. So basically we need to have a numerical solution of this. So if we consider that, gives me t is equal to 1.59362. okay, at this point ht is equal to 0.6476. So CRK LB is equal to 0.6476. Okay. If I am considering unbiased estimator, suppose I take Tx is equal to x minus 1, then expectation of Tx is equal to theta and variance of Tx is equal to 1, which is obviously greater than 0.6476. So variance does not achieve Okay, is this working clear to you? Okay, is this clear to you? Calculations are clear to you?
Yes, sir.
I will give one example where CRK bound is actually attained. So let us consider the example that we have done earlier. Say from normal θ1. What is RCLB here? Can you tell me the answer? Because this we have done earlier, this problem. What was RCLB for this problem?
So 1 by n.
1 by n, but here n is 1, so this is simply 1. Okay, this is 1 here. Now let us look at the CRK bound. For the purpose of this classroom exercise, I am taking the simplest cases. If you can take x1, x2, xn, then there is nothing wrong with that. You can just do the calculation. Only little bit more complications will be there. But because I just want to show you the calculation, so I am taking the simplest case. N is equal to 1 only. So here if I consider fx theta and fx phi, that is 1 by root 2 pi e to the power minus 1 by 2 x minus theta square. In the normal distribution, actually we have the full range, so we don't have to write 2 times. I will just write once only. So fx phi by fx theta, 1 by root 2 pi will cancel out. E to the power minus x square by 2 will cancel out in the numerator and denominator. So you will be left with e to the power a half theta square minus phi square e to the power phi minus theta x. Okay. Now we have to take the expectation of this fx phi by fx theta. So that is integral. Well, this is constant, so we can keep it outside. E to the power half theta square minus phi square. And you will have expectation of e to the power phi minus theta x, which is nothing but like the moment generating function of x at the point t is equal to phi minus theta. So this is moment generating function of x at the point phi minus theta. For normal distribution, you know the moment generating function, it is e to the power mu t plus half sigma square t square. So here mu is theta and sigma square is 1. So this is simply equal to e to the power 1 by 2 theta square minus phi square e to the power t theta, that is phi minus theta into theta, plus half sigma square t square, that is phi minus theta square into 1. So you can write the you can simplify further, but let me not do at this stage. I will do it in the next step. Then similarly, we have to consider the expectation of fx phi by fx theta whole square. So that is equal to e to the power. Now you look at the terms that we are having here. It is e to the power half theta square minus phi square. So when you take square, it will become e to the power theta square minus phi square. And here I will get e to the power twice phi minus theta x. So this becomes simply e to the power theta square minus phi square into the moment generating function at the point twice phi minus theta. So again we use the same formula for the moment generating function, e to the power mu t, that is twice phi minus theta into theta plus half and then 2 square, that is 4. So it will become 2 phi minus theta whole square. So now you consider the variance term. That is the variance of fx phi by fx theta. That is nothing but this minus the square of that. So you simplify the terms, e to the power phi minus theta whole square, that will come out, and then the other term will get cancelled out because minus this one minus that. So that is exactly the same. So this is e to the power, yeah, it will become e to the power phi minus theta square minus 1.
Sir?
Yes.
Sir, in the above line, it should be 2 phi minus theta whole square.
Now is it okay?
Yes, sir.
Okay, thank you. So now the phi minus theta square divided by e to the power phi minus theta square minus 1, which is again of the same form, that is supremum t square by e to the power t square minus 1. Okay, where now here of course t is over the whole real line. You can actually calculate, it is actually equal to 1. Okay. In this problem, variance of, I mean, x is actually unbiased estimator because I have taken only one observation. And variance of x is 1. So here CRK LB is attained. Of course, here it is the same as RCLB because the regularity conditions are satisfied. So you can calculate that also. Okay, so is this calculation okay for everyone? So some part I am putting as a star here. It means that you should just work out yourself and see the proof. Okay, because this is simple mathematical exercise. Okay, is it okay? So I am actually, we are discussing the lower bounds and we are looking at various kind of things. Actually, for those who may be just interested to know that apart from unbiasedness, what other things, what is the other use of this lower bound? So the other use of the lower bound is actually, if you look at the initial one that we obtained on the right hand side, we had in the denominator something called information. Okay. So if the information increases, the lower bound decreases. If the information decreases, the lower bound increases. Okay. So this kind of concept is actually used in information theory. So those who will be doing little bit advanced studies and advanced applications, you will see various applications of this inequality. It is also called information inequality. So there are different names and there is a lot of research work in these topics. Here in the class, I am telling something which is done in the beginning. That means in when the concept of minimum variance unbiased estimation came up, then how to find out that some methods were developed. However, it was later found out that these methods can be extended to various other kind of things. So later on, when for decision theoretic proofs were derived, that there is no estimator which is better than a given estimator, or there is no procedure which is better than a given procedure, these inequalities found serious applications. So that is why these have become popular. What I am telling here is something which was developed much earlier, I mean in 1950s and 60s. But the research work that has been done currently, which is of application to information theory and others, that is of a slightly higher level, which because most of you are from the second year only, so you will not be able to understand the concepts of that. So I will not touch those things. However, something which you can still understand, I will look at that thing. So I have discussed here one parameter. So naturally, in many distributions, we have 2 parameters, 3 parameters, etc. So is there a simultaneous lower bound? So the answer is yes for that also. That means if we are considering in place of one parametric function, we are considering several parametric functions. Then how to write down the inequality? So I'll just write it here. So suppose we have a random sample. So now theta I am taking to be a multi-dimensional parameter. Suppose it is a k-dimensional parameter. Theta is of course a subset of k-dimensional space. And another thing is that in one dimension I have considered that theta should have interval, because we need some differentiability conditions, etc. So in k dimension it should be an open ball, okay, in Rk. So we consider estimation of parametric functions so g1, g2, gr theta, okay, where r is an integer. So we consider unbiased estimators of g1, g2, gr as t1, t2, tr. So expectation of Ti is equal to Gi theta for I is equal to 1 to R. So these are all unbiased estimators. We want lower bound for variances of Ti's. So let us give some notation here. So T is, so T prime I will write as T1, T2, Tk, Tr. let the variance of Ti be equal to VII for I is equal to 1 to R, and covariance between Ti and Tj, that is equal to Vij for I not equal to j, and of course Ij is equal to 1 to R. The dispersion matrix of T is, I'll call it V. So V is V11, V12, V1R, V21, V21 and V21, they are same because of the symmetry of the covariance term. Okay. As in the case of one dimension, we need G prime theta terms will come there. So I will write here the partial derivatives so delta Ij, that is defined as derivative of Gi with respect to theta j for I is equal to 1 to R, j is equal to 1 to k. So based on that, we frame a matrix here, that is delta. So this V is R by R and delta is R by K matrix, which that is the matrix of this partial derivatives. So we write it here like this, delta 1 1, delta 1 2, and so on, delta 1 K, delta 2 1, delta 2 2, delta 2 K, and so on, delta R1, delta R2, delta RK. So this is R by K matrix. And we had the information matrix, information term was there in the case of one dimension. In the case of K dimensional parameter, it will be information matrix. So I will introduce it here. I will write Iij, it is minus expectation del 2 log of fx theta divided by del theta I del theta j for I is equal to 1 to k, j is equal to 1 to k. So when I is equal to j, this becomes the square term, that is the usual information term. So I, that is k by k. This is the matrix of these terms, I11, I12, I1k, I21, I21, I12, they will be same, and so on. So this is the information matrix. What were the regularity conditions? The differentiability of the density. So here second order derivatives will be required for the density function, and then differentiation under the integral sign with respect to all theta is, etc. So I will not list all those things under the regularity conditions. V minus delta I inverse delta transpose is a non-negative definite matrix. In particular, VII is greater than or equal to double summation IST del GI by del theta S del GI by del theta T. Where what is this term IST? It is the STth term in the inverse matrix. Where IST is STth term in the matrix I inverse. So this is the generalization of RCLB to higher dimension. I'll ask the question here. All of you are familiar with a non-negative definite matrix. Here I have used the term here. You are familiar with this term?
No, sir.
No, sir.
In your maths 2 in linear algebra, have you done that? No. Quadratic forms have you done?
No, sir.
Yes or no?
Yes, sir.
Okay, I'll just write it here. So this is some additional thing. I am just writing it here. Actually, you should look at a book of matrix theory and read from there. Okay, because you are supposed to know from linear algebra or matrix algebra. But anyway, at least for the sake of definition, I am writing it here. So a symmetric matrix is said to be positive definite if x prime ax, okay, is greater than 0 for all x belonging to Rn. That means for all real vectors x prime ax is positive number. Okay, this x prime ax is actually called a quadratic form. It is said to be non-negative definite if x prime ax is greater than or equal to 0 for all x belonging to R. Actually, there are certain consequences of this. For example, a necessary and sufficient condition for positive definite is that all the principal diagonal matrices, they are having positive determinant, and it is a necessary and sufficient condition. Another necessary and sufficient condition is that all eigenvalues are positive. Similarly, if you have a non-negative definite matrix, then a necessary and sufficient condition is that all the eigenvalues are non-negative. Another necessary and sufficient condition is that all the principal diagonal determinants will be non-negative. So from here, actually, I am saying here that V minus delta I inverse delta transpose, this is non-negative definite. Therefore, the diagonal terms, they will become non-negative. So that is why this in particular term that I have written, that VII, so that in particular it gives the lower bound for the variance of the unbiased estimator of GI theta. So this particular term, it is coming from the comparison of the ith term to ith term, that is V minus delta I inverse delta transpose. So that is greater than or equal to 0. So that is what it gives here. Okay. So I am just leaving this here, this part. A is positive definite if and only if all eigenvalues of A are positive. This is if and only if all principal diagonal determinants are positive. And the same statement is true for the non-negative also. Only thing is strict inequality will change to the strict inequality will change to equality. Greater than or equal to everywhere. There are some more properties, so I'm just putting it as a star here. I think actually in statistics, this positive definite and non-negative definite always comes there. Actually, in the multivariate normal distribution, this variance covariance matrix that is non-negative definite, and therefore all the nice properties are there. Okay. Actually, you can download this book from our library site, because in our library they are subscribing to the Springer. So from Springer Corner, you can just download the book, okay? Because Springer is subscribed by our library. So do you have any questions on this? Otherwise, I will move to the proof of this result here. Again, proof uses certain property of the matrices. So I think you may have to still read the book actually for the properties, because here I'm not writing down the proofs of those properties. So let us look at this expectation of Ti, which is the starting point. Earlier we have used it in the Bhattacharya bound and in the RC bound. So same thing here also, because the differentiation will start from the relationship that is given here. Okay. Do you have any questions? Any student is having any question? Hello, do you have any questions?
No, sir.
So as before, we have to write a multiple integral, but I will not write multiple integral. I'll just write one integral, because I will write dx kind of thing. So assuming the so you differentiate on both the sides. Okay. So this will come, and then you can actually write divided by fx theta into fx theta dx. So that is del gi by del theta j. So I am differentiating with respect to theta j here. Okay. This is nothing but delta ij. So this is nothing but expectation of Ti, and this derivative is coming here. So del log f by del theta j. So that is equal to delta ij. Once again, expectation of this term is actually d0. That is, if I consider expectation of del log f by del theta j, that is going to be 0. We have proved it earlier with respect to one parameter, but even with respect to other parameters also this will be 0. So this means that covariance between Ti and del log f by del theta j, that is going to be delta ij. So now consider the dispersion matrix of T1, T2, Tr and 1 by f del f by del theta 1 and so on, 1 by f del f by del theta k. So this is r plus k dimension. In the dispersion matrix, what are the terms you will get? You will get variances of each term. These are all here. So for each of them, you will get the variance here. Okay. Then you will have the covariance between different terms. So let me write here what kind of terms you will have. So variance of Ti, we have already written, it is VII, that we have given the definition. What is variance of these terms? 1 by f by del theta I. That is nothing but expectation of del log f by del theta I square. Earlier I have given a proof of this for one dimension. That is equal to minus, that is I11. Okay. So let me put it here j here, because I am using for the other one. So let me put j here. So this is Ijj. And covariance terms I have written here. Covariance between Ti and this term, that is delta Ij. So what will be the dispersion matrix now? It is a big matrix. I will write it like this: V delta transpose and I. These are R terms here. This is K terms here. These are R terms here, K terms. So this is R plus K by R plus K matrix. I am writing it as a partitioned matrix. I am using little bit of properties of this partition matrix. Actually, if I consider this entire thing, this is non-negative definite. If you are little bit getting lost that how I am writing big things here, that why this is non-negative definite, let me just give a very simple example. Okay, suppose I consider say uv, okay, and we write say variance of u is equal to sigma u square, variance of v is equal to say sigma v square, and covariance between u and v is sigma uv. All right. Then what is the dispersion matrix of that is sigma u square, sigma v square, sigma uv, sigma uv. You look at this term, the diagonals are non-negative, okay? And another thing that you see, the determinant is sigma u square, sigma v square minus sigma uv square, which is greater than or equal to 0 by the covariance inequality. Okay, so this is non-negative definite. So if you extend this argument to higher dimension, this will also be non-negative definite. So if it is non-negative definite, if I write down the determinant of the partitioned matrix, it is product of two terms. So what we do, we just write this result here. I am not going to write the proof of this. Okay. Okay, so I is identity matrix. Minus delta I inverse. This is information matrix inverse. Null matrix and I inverse. And V delta transpose I. So all the principal diagonal determinants will also be non-negative, because I can write it for like in place of T1, T2, Tr, I can just take T1, I can take T1, T2, I can take T1, T2, T3 and so on. The statement will remain true. So therefore, all the principal diagonal determinants will be greater than or equal to 0, which means that V minus delta I inverse delta transpose is non-negative definite matrix, which is the primary statement of the generalization of the Rao-Kramer lower bound. I will give an extremely simple application here, which of course you can verify quite simply. So I consider, say, a random sample from a normal distribution with two parameters. In the RC lower bound, I have considered normal distribution, but only with one parameter. Either I took sigma square to be 1 or I took mu to be 0. But now I am taking full model, that is with mu and sigma square. So here both mu and sigma square are unknown. So basically, what is your parameter theta? Parameter theta is consisting of two components here, mu and sigma square. So if I consider, say, function g1 theta as mu and g2 theta as sigma square, then we write for one component and then we will generalize it to the n components actually. So your fx theta, that is 1 by root 2 pi sigma square e to the power minus 1 by 2 x minus mu by sigma square. So if I take log of this, that is minus 1 by 2 log 2 pi minus 1 by 2 log sigma square minus 1 by 2 sigma square x minus mu square. So we need to consider the derivatives of this first order and then second order, because these will be required in the information matrix. So del log f by del mu, that is equal to, here there is no mu, so this will give me twice x minus mu by 2 sigma square with a minus sign. So 2 will get cancelled out. So I will get x minus mu by sigma square. And similarly, if I consider second derivative of this with respect to mu, then that will give me minus 1 by sigma square. So what is I11? That is minus expectation of del 2 log f by del theta 1 is 2. So here it is mu 2. So that is equal to 1 by sigma square. That is the first term of the information matrix that we are able to calculate here. Of course, you have to do n times because I have written for one term here. So if I am writing for x1, x2, xn, I will write n times that. Anyway, that can be written immediately. Let me write second term. So if I consider derivative with respect to sigma square, so minus 1 by 2 sigma square plus x minus mu square by 2 sigma to the power 4. So if I take second derivative here, del 2 log f by del sigma, then that is equal to 1 by 2 sigma to the power 4 minus x minus mu square by sigma to the power 6. 2 will come in the numerator, so 2 will get cancelled out. So now if I take expectation of this, it is e to the expectation of x minus mu square, that is 3 sigma to the power, that is sigma square. So 1 by sigma to the power 4. So this is with a minus sign. So minus 1 by 2 sigma to the power 4. And then there is a minus. So it will become minus minus plus. So 1 by sigma to the power 4. Sorry, 1 by 2 sigma to the power 4. And then you also have the del 2 log f del mu by del sigma square, that is minus x minus mu by 2 sigma to the power 4. So if I take expectation of that, that will be equal to 0. So your I matrix is n by sigma square 0 0 n by 2 sigma to the power 4. So I inverse will become simply sigma square by n 2 sigma to the power 4 by n 0. So the lower bound for the variance of an unbiased estimator of mu, that is sigma square by n, and of sigma square it will become 2 sigma to the power 4 by n. Okay, so are these calculations clear to you?
Yes, sir.
Okay, so probably I will do only this much in the lower bounds. I mean, we have covered primarily the Rao-Kramer lower bound for one dimension and for the higher dimension. One extension of the RCLB was to higher order derivatives, which is called Bhattacharya lower bounds. And we have seen some calculations based on that. Another extension of RC lower bound is when we don't put any regularity conditions, that is the Chapman-Robbins-Kiefer lower bounds. Okay. As I mentioned to you that in the statistical decision theory as well as in the information theory, it is an active research area actually, finding out the lower bounds and having certain applications of that in proving some other results. So those who are interested, actually you can look at, I have given you several references in the first lecture. When we circulated the syllabus, if you see at the end of the syllabus, there is a list of books. So you can explore those books and get a lot of information about that. I mean, especially those who are interested into deep theory of this. So you can look into that thing. So you can just search like in the Google Scholar, Rao-Kramer type inequalities or Rao-Kramer bounds and so on. You will find hundreds of research papers on that. So probably I will stop this topic at this point of time and we move to something else. Especially this concept of information has another extension. This is another understanding in statistics, and you can actually see that the present definition of information which is used in signal processing, in electronics and in communication, actually that is a follow-up of the definition which was given in statistics. So statistical definition actually precedes the information definition which is prevalent now in the science and engineering. So the next concept I will take up now. So maybe I can give a break for a few minutes now. Maybe just 5 minutes break you can have, and then I'll proceed further. Okay. So now I will discuss the principle of sufficiency. Okay. So firstly, let us look at the formal definition of this one. So let x1, x2, xn, okay, be a random sample, say from a population with distribution fx theta. Okay. So this could be your PDF or PMF. Okay, it could be either. So x is x1, x2, xn. Okay, so we say that a statistic T is sufficient for this family of distributions if the conditional distribution of x1, x2, xn given Tx is equal to T is independent of theta. So this is the formal definition. I will explain this. What does it mean? Okay. Okay. So first of all, what is the literal meaning of sufficiency? What do you mean in English language by something called sufficient? Okay. So like you say that this much food is sufficient, or this much books are sufficient, or anything. I mean, any quantity of something is sufficient. It means that that is enough for the purpose for which it is desired. So like if you say that a certain amount of food is sufficient, that means it is sufficient for satisfying your hunger. Okay. If you say that certain quantity of certain item is sufficient for your purpose, that means for that purpose it is enough. I mean, you may have something more, but it is not required. Even if you don't have that, that is enough. So sufficiency in a literal meaning, it means that if apart from that something else is not available, even then your required objective is met. So that concept has been transformed to statistics in such a way that you have a sample x1, x2, xn, but now I am calling a function of x1, x2, xn, that is a particular statistic. Now I am calling it is sufficient if some condition is satisfied. Okay. That is the conditional distribution of x1, x2, xn given T is independent of theta. So now in a statistical inference problem, you have x1, x2, xn as sample. For what purpose it is used? The purpose of the sample is to get certain information on theta. That means we want to either estimate theta, or we want to do some testing of hypothesis for theta, etc. So this concept tells that if I have a sufficient statistic, then I did not keep record of all the values of the x1, x2, xn. So as such, it doesn't look a big thing. But if you look at from practical point of view, that for example, you have 1000 data, or you have 10,000 data, or you have 1,000,000 data. Okay, but a certain purpose is to be served. For that purpose, if I have one statistic T, which is a function of x1, x2, xn, and I get the value of that, then that is enough. I don't need to keep the record of all the observations. Okay. Now statistically, let me again explain this. This signifies that if one does not have original observations but has T and a knowledge of known conditional distribution of x1, x2, xn given T is equal to T. Then one can generate xn prime which have the same distribution as x1, x2, xn. So this is basically principle of data reduction. So let me explain it through some example so that immediately it becomes clear. Let me start with the simplest example. Let x1, x2, xn be random sample from Bernoulli distribution with parameter p. Okay. In Bernoulli distribution, what this parameter p represents? In the Bernoulli distribution, what the parameter p represents? Anybody can tell me?
Probability of success.
Probability of success of what?
Desired event.
Of the desired event. Okay. If I have the value x1, x2, xn available to me, that means I have n trials and I have record of that. For example, in the first trial, there is a win. In the second trial, there is a win. In the third trial, there is a loss. In the fourth trial, there may be a loss and so on. So out of the n trials, I have certain information which trial resulted in success and which trial resulted in failure. In order to draw certain inference on P, what do I need? Suppose I want to say something about the parameter P, then if I have the original values of x1, x2, xn to me, that means either they are 1 or they are 0. How will I use them? Yes, anyone? Yes, Venkat.
So we can use them for in the statistic which we have.
What
we
is that
can do-
statistic? Yeah, what is that statistic which we'll use? Like I have the values of x1, x2, xn, but I want to say
X bar.
something about P. Yeah, what did you say?
X bar.
X bar. X bar is basically sigma xi by n, isn't it?
Yes, sir.
That means out of n observations, how many, what is the proportion of success? Isn't it? Sigma xi by n is basically proportion of success. So you want to say that individual xi's do not contribute to my additional knowledge. If I want to have certain knowledge about P, it is enough if I have sigma xi or sigma xi by n to available to me, isn't it? That is what you are saying?
Yes, sir.
Okay, so that's good. So that means for the purpose of making any inference on P, it is enough if I have sigma xi available to me. That means out of n trials, total number of success, isn't it? Like if we are looking at a match of say basketball or a match of, or even a tournament like we look at kabaddi, or we look at tournament of cricket and so on. So for example, if there are 5 matches, then we look at what is the outcome. That means which team won more matches, isn't it? 3-2, 4-1, 2-1 and so on. Some kind of result will be there. That is enough to tell me the result of the, what is the proportion of winning. Okay. It is not very important to keep the track of each of them, because if I am looking at, if my parameter of interest is only the proportion of success, then sum is enough. So here we will then consider here we will show that, say, T is equal to, say, sigma xi is sufficient. That means the conditional distribution of x1, x2, xn given T is equal to T. So that is conditional distribution of x1, x2, xn given T. I should show that this is free from parameter P. Okay. So, okay, this is conditional probability. So I can write down the definition. Conditional probability is joint probability, that is probability of A given B is probability of A intersection B divided by probability of B. Okay. So here actually this T is nothing but sigma xi. So if I am putting x1 is equal to small x1, capital X2 is equal to small x2, capital Xn is equal to small xn, then this T must be equal to sigma xi. Otherwise this statement has no meaning. It should be basically 0 in that case. So I can put it like this. This is equal to probability of x1 is equal to x1, x2 is equal to x2 and so on. Xn minus 1 is equal to xn minus 1. Xn is equal to T minus sigma xi, I is equal to 1 to n minus 1 divided by probability T is equal to T if this T is equal to sigma xi, I is equal to 1 to n. Otherwise it is 0. Okay. Here I have taken x1, x2, xn to be a random sample. That means they are independent and identically distributed random variables. So in the numerator I have this joint probability. This will become product of the individual terms. Here x1, x2, xn are IID, Bernoulli, P. So sigma xi, that is T, that follows binomial NP. So I can then write the above term as, so this term. So that is equal to probability of x1 is equal to x1 and so on. Probability of xn minus 1 is equal to xn minus 1. Probability of xn is equal to T minus sigma xi, I is equal to 1 to n minus 1 divided by probability of T is equal to T. Is this step clear? I have written only the non-zero term. The zero term I am not writing again.
Sir, can you say why it is becoming 0 if T is not equal to that? Like it can have.
This is conditional probability here. So if this small t is not equal to x1 plus x2 plus xn, then this event will become null event. That is the empty set. Because capital T is capital X1 plus capital X2 plus capital Xn. If the values of x1, x2, xn are fixed as small x1, small x2, small xn, then capital T must be equal to the sum of those values. So this small t must be equal to the sum of those. If it is not, then this becomes an empty event. So in that case, it should become equal to 0. So only 2 possibilities are there. Is that
So
okay?
is that a convention? Like since it is not equal, we say that empty.
No. There is no convention here. No, there is no convention. I am identifying the set. When is this capital X1 is equal to small x1 and so on, xn is equal to xn and t is equal to t? Under what condition this will be true? Where capital T is defined as the sum of xi's. That is defined only if small t is equal to the sum of small xi's. Otherwise, this event will convey a null event, isn't it?
Yes, sir. Okay.
So now just write down these values because these are Bernoulli. So this is p to the power x1, 1 minus p to the power 1 minus x1 and so on, p to the power xn minus 1, 1 minus p to the power 1 minus xn minus 1, p to the power t minus sigma xi, I is equal to 1 to n minus 1, 1 minus p, one minus p to the power 1 minus t plus sigma xi, I is equal to 1 to n minus 1. That is the numerator term. And the denominator I don't calculate here because this is nothing but binomial. So it will become nct p to the power t 1 minus p to the power n minus t. So just look at the terms. Every term get cancelled out. You are left with only 1 by nct. So by our definition of sufficiency, sigma xi is sufficient. For the Bernoulli family, this is sufficient. So if we consider the physical meaning of sufficiency or the literal meaning of sufficiency, and we look at this corresponding statistical definition, there is some sense of justification for the definition. Because what you are saying now that sigma xi is sufficient. So for doing any inference on P, it is enough if I have sigma xi. I need not keep the record of individual trials, isn't it? Suppose I am looking at what is the proportion of heads if I am considering what that means. I am looking at the probability of head in the coin tossing experiment, and suppose 10,000 times the experiment has been conducted. Then we just look at the ratio of the number of success. That's all. That is enough for me. I don't need to keep the track that in the first trial there was head, in the second one there was a tail, and so on. That entire sequence of that is immaterial. You can look at it in this way. At the end of a cricket match, there is a summary statistics. So for example, for a batsman, they will write he faced these many balls and he scored these many runs. So they write something called a strike rate. Now out of that, he might have scored say 2 runs in some balls, 4 runs in some balls, no runs in certain balls, and so on. But if you look at the total number of runs scored compared to the total number of balls that he faced, that is the strike rate, and that is enough for the efficiency of that batsman. That means how much good he was. Like he played well, he scored runs at a brisk pace or low pace, and so on, kind of thing. Similarly, for the bowlers, we have that in how many balls they get, how many runs. So they have something called economy rate, or they have the strike rate for the bowlers also, that in how many balls they took, how many wickets, and so on. After how many balls he gets a wicket, and so on, isn't it? So summary statistics helps to provide that what is the contribution of individual players, and you don't need to look at each and every ball, and that complete record is not required. Okay. So I will take another example, which is again a very similar example, and you can appreciate that also, in the sense that you can actually tell me that what will be sufficient statistics without my calculation. So suppose I am considering Poisson lambda distribution. Lambda is positive. So what does it denote? X1 denotes a number of occurrences in a Poisson process. X2 denotes the number of occurrences in a Poisson process. I have taken lambda here, so lambda t I am not writing, but it is understood. It could be number of incidents, number of arrivals, and so on. So I have n data points here. So it could be something like that on n different dates, how many arrivals are there. And I have to draw certain inference on lambda, where lambda is the rate of occurrence, or the rate of arrival, or the rate of incidence, etc. So what do you feel is sufficient, or what do you feel will give me information about lambda if I have the data available to me in the form of x1, x2, xn? Let me ask someone, say, let me call names of some students here. Is Keshav Reddy there? Keshav Reddy? Oh, some students there, I think, just keeping it on and not present. Okay, let me ask Astha Banjare. Priyanshu Kumar. Okay, nobody is there. I'm not hearing anyone. Nirbhay Kumar.
Yes, sir.
Yeah. What do you feel will be a sufficient statistics in this problem, and why? Did you follow my
I'm not-
question?
Yes, sir, but I'm not getting.
Okay, let me ask someone else. Vismay Parija. Hemant Rao.
Sir, I think X bar.
Okay, why?
Sir, like as done before, we can directly put like probability of x1 equals to x1 into so on until the probability of xn minus 1 equals to small x1 minus 1 into probability of.
No. That is, you are telling the proof. I'm not asking the proof here.
Yes, sir.
In this problem, why x bar should be sufficient? I'm not asking the proof of that which we gave for binomial.
Okay,
I'm
sir.
just asking the direct question. Literally, why should sigma xi or x bar be sufficient in this problem?
Sir, because
Yes.
sir, I'm not getting, sir.
Okay. Anybody else would like to answer?
So the mean of Poisson distribution is lambda. So
No, that is all right. That is all right. Mean of Poisson is lambda. So that you are telling like unbiased estimation and all that we have done. Why this should be sufficient? So sufficiency is a different concept. No, here I am saying that it contains the information which is available for lambda from the sample. Okay. So why should sigma xi or x bar in this problem should have all the information? That is my question. Theoretically, we will prove it. That's not a problem. We will prove it because the proof will be similar to the one which I gave.
So it will tend to binomial will tend to Poisson.
No. Forget about binomial. Here I am not talking about binomial. This is Poisson case. What is the physical representation of x1, x2, xn?
Exponentials.
Exponential.
I mean,
Okay, anybody else would like to answer here? Vijay Kumar?
Sir,
Yes.
suppose let the Poisson distribution denote the number of accidents occurring in a road. Then we, for a year, we actually denote the average number of accidents per day, sir.
Yes.
So I thought that X bar would be sufficient.
Yeah, because you have data on certain number of days. From that, you look at what is the average or the rate of accidents. And since you want for the whole year, you take it as a representative. So this should be sufficient. If we keep a record of different days and how many accidents took place, that is not providing any additional information, because summarized information will give you the rate, because rate is required. So total number of accidents which took place vis-a-vis that what is the total duration that you are considering, that gives you the rate. So from the sample, if I look at individual ones, like on the Monday how many things happened, on Tuesday how many things happened, that is not giving any additional information. The total number of accidents that took place during that time period, that is enough to give me the rate. So therefore we will say that sigma xi or x bar will be sufficient statistic here. So theoretically, let us prove it here. Of course, the proof is almost the same as the one which I gave for the Bernoulli case here. So we will again show that T is equal to sigma xi, I is equal to 1 to n is. So you are saying x bar. So x bar is a one-to-one function of sigma xi. So it is enough if I prove for this one, because the writing of proof is easy for sigma xi here. So we consider the conditional distribution as before. So that is equal to, again, it is x1 is equal to x1 and so on. Xn minus 1 is equal to xn minus 1. Xn is equal to t minus sigma xi, I is equal to 1 to n minus 1, divided by probability t is equal to t. If t is equal to sigma xi, I is equal to 1 to n, and it is equal to 0 if t is not equal to sigma xi. So this is same logic what I wrote just now, so I am not explaining again. If x1, x2, xn are Poisson lambda, what is the distribution of sigma xi? Poisson is additive, so this becomes Poisson n lambda. And x1, x2, xn are independent, so this becomes product here. I am writing the first term only. x1 is equal to x1 and so on. Product probability xn minus 1 is equal to small xn minus 1. Probability of xn is equal to t minus sigma xi, I is equal to 1 to n minus 1, divided by probability t is equal to t. So these are all e to the power minus lambda, lambda to the power x1 by x1 factorial and so on, e to the power minus lambda, lambda to the power xn minus 1 by xn minus 1 factorial, e to the power minus lambda, lambda to the power t minus sigma xi, I is equal to 1 to n minus 1, divided by t minus sigma xi, I is equal to 1 to n minus 1 factorial, divided by e to the power minus n lambda to the power t, divided by t factorial. So if you look at this one, e to the power minus lambda, it is coming n times, so e to the power minus n lambda cancels out, and lambda to the power x1 plus x2 plus xn minus 1 plus t minus sigma xi, so you get lambda to the power t, so that also gets cancelled out. So you are left with only t factorial, and this 1 by n to the power t will come. So 1 by So let me write it like this: t factorial divided by x1 factorial, x2 factorial, xn minus 1 factorial, t minus x1 minus x2 minus xn minus 1 factorial, and 1 by n to the power t. So you can see here that there is no lambda appearing here. So if I am considering the family of Poisson distributions here, then this is a sufficient statistics. So in statistical inference, the sufficiency has a special meaning. It means that I can ignore the complete data set in favor of sufficient statistics. If I keep track of only the sufficient statistics, that is enough for the purpose of our discussion. That means whatever inference I want to draw on the given parameter, then this is okay for us. We don't need to keep all the observations available to us.
Sir,
Yes.
so here we are for finding the probability apart from lambda, we also, I mean, in the equation we also have x1 factorial, x2 factorial, and so on, xn minus 1 factorial, right?
Yeah.
So doesn't the x1 and so on till xn minus 1 represent the data for each day if we consider some accidents or something?
It represents the data. So what I have written here, I have written the conditional distribution of x1, x2, xn given t. So that is why x1, x2, xn will appear in the form of the probability distribution. They will appear here in the form of the distribution. Okay. Now, if t is given to us, okay, I will show you later on that part. I mean, that how do we use that information? See, this is the conditional distribution here. So what we are saying that if the value of t is given and this form of the conditional distribution are given, so what is the condition here? That's why I wrote that condition, sigma xi is equal to t. Okay. So now if I suppose I say t is equal to 10, x1 is equal to 4, x2 is equal to 1, x3 is equal to say x3 is equal to say 2. So this is 7, and suppose I put x4 is equal to 3. Okay. And here n is equal to 4. So here what is the sum here? 4 plus 1 plus 2 plus 3, that is equal to 10. Okay. So suppose I have value of t is equal to 10 available to me, and I know how many observations, that is 4 observations are there. Now if I write in place of this, I write x1 is equal to 2, x2 is equal to 2, x3 is equal to 2, and x4 is equal to 4. Will this give any additional information to me for lambda?
Okay,
This
sir.
it will not
Yes,
give
sir,
any. So I can generate many samples which will give me the same information, isn't it?
Yes,
I
sir.
can change the values, but it doesn't lead any extraordinary thing here. This is the same thing. Like you are only telling that in the, like here, if I say it is the number of accidents on 4 different dates. So on first day there were 4 accidents. In the second sample, in the first day there were 2 accidents, and so on. What is important is that in the total duration in the week, there were 10 accidents are on the 4 different days or whatever you are saying. So the rate, for the rate purpose, this is enough for me, isn't it?
Yes, sir.
I think I may stop at this point. Okay, so we have, I will tell you, because this method is like I explained as in a heuristic sense, that what do you think, what is sufficiency, and then we gave some sort of definition for that. Now we will see that what is the proper methodology, and then what are the consequences of this definition of sufficiency in terms of retaining of the information, in terms of unbiased estimation, and so on. So all those things we will see in the next class. Okay. Do you have any more questions to me? Do you have anything else to ask? Otherwise, I'll stop the class now.
So in last week's RCLB calculations, when you had given us 4 examples to do, in each of the the 2 cases where the normal distribution was given, you just directly looked at it and you gave us the result. So is there a short way to do it, or is the long calculation is the only way?
No, calculation is the same. Only thing is, see, this is experience only. That's all. I mean, because I know those things, so that's why I am telling. I mean, once you are familiar with this, actually, the way I am doing this inference course, I want to bring out certain structural properties of the distributions. So that is why I am doing in a particular sequence here. Like I gave you maximum likelihood estimator. So we wrote something called likelihood function. So you learned how to write down the joint distribution of certain, like if I say x1, x2, xn. So for normal distribution, how do you write? For Poisson distribution, how do you write? For and then I also gave you the form of something called exponential family of distributions. Now, from there again, this Rao-Kramer lower bound, when you are calculating, again the same type of terms are being utilized, that fx, theta, and so on, isn't it? So again, you write all of them and then you differentiate and put equal to 0, take logarithm, and all those kind of things. So once you are familiar with that, then for a lot of these questions, you will be able to answer immediately, because basically you will become familiar with the terminology. So statistics should not be something like which is very, very difficult and like you have to just get something, solve a lot of equations and then get something. It should actually appeal to the common sense. That means the usual frequently used procedures, those procedures should be sort of common sense thing. Only thing is now we are formally justifying all of them. For example, as I think somebody said that in the binomial example, that for proportion estimation or for inference on proportion, it is enough if I have x bar. Yes, a layman will think like that. Now we are giving a full justification that yes, it is okay to use the proportion. It should not be something else that somebody else comes and does some lot of calculations and gives something else. Similarly, in the Poisson example, also somebody said that, okay, we should use sigma xi or x bar. Yes, I am justifying that. So the statistical procedures that we are developing actually try to justify or try to give a formal scientific foundation to what is common sense. So common sense is, okay, use means, use variances, use medians, and so on. So we actually study the properties of those things. So that is why once we are familiar with that, you will also be able to write the answers immediately. Of course, you see, if you are new, you have to actually do the calculation, RCLB or whatever other things are there. But since I am familiar, I am immediately able to tell the answer. Okay. Because the term that sx theta and that t thing was coming, so I could just look at it and tell me. So that is because of the experience that I am having. Okay.
Yes, sir.
Okay, somebody is asking the question about the tutorial. So I actually mentioned that I will give some tutorial sheets, but I delayed it. What is happening is that most of these things, because they are coming under the same setup, since I am anyway solving so many problems only, in every class I am actually solving the problems. And you should also solve those problems again and again. So maybe actually the problem set will be like, if I give normal distribution, say with parameter mu and sigma square, then all cases you get the unbiased estimator, consistency, then you get RCLB and so on. So everything will be done, the method of moments estimator. So I was trying to write down an exercise sheet in which everything will be there for each one. So maybe this week I will prepare the full thing and give you. Okay, so I delayed intentionally because all those things are similar. Okay, because for each distribution you will have to do everything. Okay, fine.